Good evening, everyone. In today's class, we are going to discuss the last topic in this chapter heat transfer. Heat can be transmitted from one place to another by three modes. They are conduction, convection, and radiation. Methods of heat transfer, there are three methods: conduction, convection, and radiation. Conduction, the moment of heat within a object is called conduction. Conduction also occurs when objects are touching each other. Convection, the transfer of heat from one region of a fluid to another due to the movements within the fluid is called convection. So, in the same diagram, I am trying to show all the three: conduction, convection, and radiation. Conduction you can observe in the handle. As your vessel gets heated up, even the handle is going to get heated up because of conduction. The movement of heat within the object, the heat is going to move. It is called conduction. This will occur only when the objects are touching each other. Convection is going to be the transfer of heat from one region of a fluid to another region due to movement within the fluid. Movement within the fluid, that is called as convection. Radiation. Radiation is the transfer of energy through electromagnetic waves. If the energy is transmitted through electromagnetic waves, that is called radiation. Moving on, conduction. The phenomena of heat or the phenomena of transfer of heat from one part of body to another in the direction of fall of temperature without any actual movement of the particles is called conduction. If you heat up a scale, as it gets heated up, the heat is going to transfer from the hotter end to the colder end. So after a few minutes, even your hand will start burning, right? Why is this going to happen? Because of conduction. Next, when one end of a solid is heated, the atoms and molecules of the hotter end start vibrating with greater amplitude. So whenever I take a scale or any object and I start heating up that object, the atoms and molecules at this particular end will start vibrating due to the energy which is going to be supplied in form of heat. Due to this, they will transfer the same disturbance to neighboring molecules as well. So if the first molecule is going to get heated up or is getting vibrated, that is going to disturb the second molecule. Consequently, second molecule is going to disturb the third and the chain is going to continue. As a result, the energy is transmitted through the solid and the temperature of the solid increases. Substances differ considerably in their ability to conduct heat. Accordingly, solids are classified as conductors and insulators. Thermal conductors and insulators. Materials which allow heat to pass through them are called thermal conductors. Materials which do not allow heat to pass through them are called thermal insulators. Examples of thermal conductors and thermal insulators are as follows. You can have copper, aluminium, gold. Basically, most of the metals are thermal conductors. Foam, wood, plastic, paper are few examples of thermal insulating. Moving on, thermal conductivity. Consider a slab of uniform cross-sectional area A. We have a slab having a cross-sectional area A. Let me take the length of the slab to be L. Let one of its face be at the temperature T1. One of the face is at the temperature T1 and the opposite face be at the temperature T2. If one of the end is taken as T1, the other temperature is taken as T2. Let me consider T2 to be greater than T1. Then experimentally it is found that the amount of heat that flows from the hotter phase to the colder phase, from the hotter phase to the colder phase, is going to be directly proportional to the area of cross section A, directly proportional to the temperature difference delta, which is T2 minus T1, directly proportional to the time T for which the heat flows, inversely proportional to the perpendicular distance between the two faces, which is going to be L. If I have to write the same in terms of formula, I can take the amount of heat as Q is going to be directly proportional to the area A. So I can take A over here, right? Directly proportional to the temperature difference delta, which is delta T, which is going to be T2 minus T1. So I can write T2 minus T1 multiplied by small t, which is going to be the time, and inversely proportional to divided by L, which is going to be the length between the perpendicular length between the faces. So if this is one face and this is one more face, the perpendicular length between the two faces is going to be equal to L. Q is going to be directly proportional to A, delta T, and T inversely proportional to L. I can write Q as directly proportional to A multiplied by T2 minus T1 multiplied by T minus, sorry, divided by L. Now, to remove this proportionality sign, I can add a constant. Upon doing the same, I will be getting the constant as K. Rather, I will be taking the constant as K. That constant is called thermal conductivity. Thermal conductivity of a material is defined as the rate of flow of heat during steady state per unit area of the surface normal to the direction of heat with unit temperature difference. If I send T to the other side, I can write Q is equal to, I can introduce a constant which is K, which is going to be your thermal conductivity, and A multiplied by T minus T1, T2 minus T1 multiplied by the time T divided by L. This is what I will be getting when I take the equal to sign. In order to take the equal to sign, I need to introduce a constant. That constant is called thermal conductivity. And thermal conductivity is defined as the rate of flow of heat during a steady state per unit area of surface normal to the direction of heat with unit temperature difference. If the temperature difference is 1, so I can take my values of A as 1, delta T also as 1, time can be taken as 1 as well. If I consider all the variables to be 1, then I will be getting the value of K as Q. Thermal conductivity is going to be equal to the heat supplied. If we consider unit cross-sectional area, unit time, and unit temperature difference. Let me consider a problem based on the same topic. Problem number 1. Unit uniform metal rod of cross section 3 multiplied by 10 raised to the power minus 4 meter square has two holes 0.05 meter apart. One end of the rod is soldered to a steam chamber. Around the other end, a steady circulation of water is maintained. When the steady rate of flow of water is 0.77 kg per minute, the temperature difference between the water entering the circulation and leaving the circulation is 1.5 degrees Celsius. If two thermometers read 56 degrees Celsius and 42 degrees Celsius, calculate the thermal conductivity of the metal. CW, which is going to be, what is CW? Specific heat of water. It is given as 4200 joule per kg Kelvin. All right. Now, let me start the problem by writing down whatever they have given in the question. I can see that they are talking about cross sectional area. I can write A as 3 multiplied by 10 raised to the power minus 4 meter square. I have my value A. Next, we have two distances which is 0.05 meter apart. What is going to be the distance? Can I take distance to be L? L can be taken as 0.05, right? Next, whereas steady state any other number is given 0.77 kg per minute. What is going to be this? This is going to be the mass of water that is going to be flowing, right? So I can write m is going to be 0.77 kg per minute. That is the rate of water which is flowing. Let me take m as 0.77. Next, cw is also given. Let me write cw as 4200 joules, of course, per kg kelvin. Next, they have given two temperatures, right? They have given two temperatures. Also, they have given delta T. Yes, the delta T, the change in temperature, it is going to be 1.5 degrees Celsius. However, T2 and T1 are given. T2 can be taken as 56 degrees Celsius. T1 can be taken as 42 degrees Celsius. These are the data which are given in the question, right? Now, let me start solving the same. I know that the heat Q is going to be given by mc delta T. This is going to be the formula for heat. Q can be written as m. M is 0.077 multiplied by C. C is going to be Cw. It is going to be for water, 4200 multiplied by delta T. This can be taken as delta T. Delta T is going to be 1.5. 1.5. When I multiply everything, Q, I will be getting it as 485 joule per minute. Q I have got as the heat is 485.1 joule per minute. Now I can write the formula for conductivity, which is given by K is going to be Q multiplied by L divided by A multiplied by T2 minus T1 multiplied by T, which is your time. K can be written as Q I have got as 485.1 multiplied by L. L is going to be the length, right? Sorry, this one. 0.05 divided by area is going to be 3 multiplied by 10 raised to the power minus 4 multiplied by T2 minus T1. 56 minus 42. The answer is going to be 14. T2 minus T1 is going to be 14 multiplied by T. What is going to be your T? Per minute we have got. Per minute. So I should be writing the SI unit. SI unit of time is second. 1 minute can be taken as 60 seconds. Taking the time as 60 seconds, I will be getting 60 over here. When I simplify, I should be getting the value of K as 96.25. It is going to be Weber per meter per Kelvin. This is going to be the final answer. Let us take one more question. A man wraps himself in a funnel 4 mm thick. How much heat will be lost per square meter of his body per hour if the atmospheric temperature is 20 degree and the body temperature is 37 degree? The coefficient of thermal conductivity of the flannel is 0.05. That is what is given in the question. Okay. What is a flannel? Do you know? It is kind of a jacket. Okay. Let me start by writing what is given in the question. I have, or I can start with L, right? The length. What is the length given? It is 4 mm. It is 4 mm. I have to take the SI unit. SI unit is going to be meters. So I can write this as 4 multiplied by 10 raised to the power minus 3 meters. This is going to be the value of L. L I have got. Next, what do I have? I have the temperature which is 20 degree and 37 degree, right? So I can write T1 as 20 degrees Celsius, T2 as 37 degrees Celsius. I can convert this into Kelvin as well. If I convert into Kelvin, what will be the value of 20 degree? I need to add 273, right? If you want to convert degree Celsius to Kelvin, then you have to add 27. 20 degrees Celsius into Kelvin, I need to add 273. The answer is going to be 293 Kelvin. If I add 37 to 273, what will be the answer? It will be, how much is the value is going to be? Sorry, 320, 320 or 310? What is the value you'll be getting? 310? It is going to 310 or different. It is going to be 310 Kelvin, right? Plus 273. So I have got the values of T1 and T2 as well. Let me see what else value is given. 0.05. What is going to be this? 0.05. It is going to be K, right? Thermal conductivity 0.05. These are the data which is given in the question. Now let me write the formula for the heat. What is asked? How much heat? So Q is given by the formula Ka multiplied by T2 minus T1 divided by, of course we have T as well, divided by L. This is going to be the formula, where Q is going to be the heat, K is going to be the thermal conductivity, A is going to be the cross-sectional area, T2 minus T1 is going to be the temperature difference, small t is going to be the time, L is going to be the length. In this case, we can consider that as thickness. Substituting the same, I will be getting the value of Q as 0.05 multiplied by, it is, what is the area given? The thickness area is per square meter, per square meter. So this is going to be multiplied by per square meter, it is 1 itself, multiplied by T2 minus T1, 310 minus 293, multiplied by the time. What is going to be the time? It is going to be per hour. 1 hour is going to have 60 minutes. SI unit of time is going to be seconds. So I need to represent hours in seconds. 60 minute or 1 minute is going to be, 1 minute is going to be 60 seconds. So I can write 1 hour is going to be 60 multiplied by 60, which is going to be 3600 seconds. 3600 whole divided by the value of L, which is going to be 4 multiplied by 10 raised to the power minus 3, because I have to take it in SI units. Substituting all the values, I will be getting 0.05 multiplied by, what is the temperature difference? It is going to be 17 multiplied by 3600 divided by 4. And here you can write 10 raised to the power 3. I am taking 10 raised to the power minus 3 to the numerator. It is going to become plus 3. When I substitute the value, yes, I need not substitute, I just need to simplify the values. The final answer, I should be getting it as 1.12 multiplied by 10 raised to the power 3 joules. This is what is the final answer. Moving on to the third problem. It is also similar to what we have considered just now. The lower surface of cubical slab stone of side 0.1 meter is exposed to steam at 373 Kelvin. A thick layer of ice, I'm sorry, yes, a thick layer of ice covers the upper surface. The other faces are covered by non-conducting material. In 40 minutes, 0.15 kg of ice melts. Find the thermal conductivity of stone. Latent heat of ice is given as 3,36,000 joule per kg. Let me start by writing whatever they have given in the question. They are talking about the side length, which is going to be L 0.1 meter. Since it is in meters, I need not change anything. Next, the temperature is given. It is 373, right? Lower surface of a cubical slab stone of side, the side I have taken, is exposed to steam at 373. A thick layer of ice covers. So if steam is at 373 and the other is of ice, this is going to be the higher temperature, right? So T2 is going to be 373 Kelvin. All right. What is going to be T1? T1 is going to be ice. What is the temperature of ice? It is going to be 0 degree, which is going to be 273 Kelvin. I have got T1, I have got T2, L, they have already given in the question. Next, time is also given. Is time given? T is going to be 40 minutes. If it is 40 minutes, converting into seconds, I can multiply with 60. 40 multiplied by 60, T is going to be 2400 seconds. The value of T also I have got. M is given the mass. It is in kgs, so I need not change anything. I can keep it as it is. Also, the latent heat of ice is also given in the question itself. So I will not be making a note of the same. Everything other than that, whatever is given in the question, all the data I have taken. What I need to find out? I need to find out the thermal conductivity. Let me write the formula for the same. Thermal conductivity is given by K, which is going to be equal to Q multiplied by L divided by A multiplied by T2 minus T1 multiplied by T, which is going to be your time. Substituting all the values, K is going to be equal to Q. What is the Q over here? Anyone? Q we need to find out. We don't know the value of Q, right? Q we need to find out the value of Q. What is the formula for Q? It is going to be ML. Q can be taken as, when I find out the value of Q, it is going to be 0.15 is the value of M multiplied by 3,36,000. So 3,36,000, that is going to be the latent heat of ice. Q value, I will be getting it as, or I can keep it as it is. The same thing I can be substituting over here. Q value as 0.15 multiplied by 336,000 multiplied by L. The value of L is going to be 0.1 whole divided by A. The value of A. What is your A value? Have they given? It is zero point 0.1. So zero point 0.1 multiplied by zero point 0.1. The value of A is not given. L value is given. If the length is given, you can just multiply the length or take the square of the length. You will be getting the area multiplied by 373 minus 273 multiplied by 2400. Right? Now I can cancel out these two zeros and these two zeros first. 373 minus 273 is going to be 100, right? K, I will be getting this as 0.15 multiplied by 336 multiplied by 0.1 can be cancelled again. So I need not take 0.1 over here. It is divided by 0.1 multiplied by 100. 0.1 multiplied by 100, 0.15 multiplied by 336 divided by 0.1 multiplied by 100, right? when you take when you simplify the values, you will be getting over here zero point 0.1 multiplied by 100 is going to be 10. Yes, 10, right? Okay, 336 multiplied by 0.15, 5 multiplied by 6 30, 31 3 carry, 3 multiplied 336, 0 0 1 carry, 4 4 1 carry 5. So you will be getting the value as you two. Okay, sorry, we have 24 also here, right? Yes, 24 also we have. So let me write 24 over here, and here I'll be taking the value as 0 point, which is 50.4. Finally I will be getting the answer as, yeah, k, which is going to be 50.4 divided by 240, divided by 240. Anything else I have missed? K is 53.6, 10 to the 10 raised to the power 3. It is over. Okay, this is 3360. Okay, 10 is there, so this can be taken as 504. This is 504. 504 divided by 240, so around 2 times 2, 2.1, right? Approximately k is equal to 2.1. Unit is going to be Weber per meter per Kelvin. This is going to be your. Let us move to the fourth problem. A copper rod and an aluminium rod of equal length and that is not reception area, it is cross sectional area. Let me make the change. Cross-sectional area are soldered end to end. The free end of copper is at 373 Kelvin and free end of aluminium is at 273 Kelvin. If conductivities of copper and aluminium are given as 385 and 180 Weber per meter per Kelvin, find the temperature of interface under steady state. Temperature of interface meaning that we have to find out T at this point where both of them meet. This is the question, right? Now let me take this as 1 and this as 2. Object 1 and object 2, they have given equal length, right? So I can write length 1 is going to be equal to length 2. I will be starting with this, right? Next, the temperatures are given. T1 is going to be 273 Kelvin. T2 is going to be equal to 373 Kelvin. The temperatures are also taken down. Next, I can write the values of conductivities. Copper, it is taken as 1. Conductivity is K. I can write K1 as 385 and K2 as 180. I have got the values of K1 and K2 as well. Now, let me write the value of Q. What is the formula for Q? Q can be written as Ka multiplied by T1 minus T2, right? Multiplied by T divided by L. Substituting or taking the value of Q1 and Q2, I will be getting the value of Q1 as K1 A1 multiplied by T2 minus T1 multiplied by T divided by L1. Similarly, I can take Q2 also, which is going to be K2A2 multiplied by T2 minus T1 multiplied by T divided by L. multiplied by L. Now, this can be taken as equation number 1. This can be taken as equation number. Let me go to the question. We need to find the temperature of the interface at steady state, meaning that at this point we need to find the temperature. So here the temperature will be the same, right? Yes or no? Meaning that the heat from here and whatever the heat from here, it has to attain thermal equilibrium, right? At that point you will be having q1 is equal to q2. q1 will be equal to q2. This is the condition for thermal equilibrium. Condition for thermal equilibrium. Equating 1 and 2. From 1 I can take the value of q1, and from 2 I can take the value of q2, equating the same. If q1 is equal to q2, then that can be written as k1 a1 multiplied by t2 minus t1 is going to be multiplied by t also is going to be equal to k2 a2 multiplied by t2 minus t1 multiplied by t whole divided by, this is your L1, this is going to be your L. Now I can cancel out whatever is common. Since the lengths are the same, since the lengths are the same, the length can be cancelled, right? Since areas are all those also the same, cross sectional area, right? Equal length and cross sectional area are also the same, so I can cancel that out as well. And time, for both the time is the same, whether it is aluminum or copper, the time is going to remain the same. I will be left out with k1 multiplied by t2 minus t1 multiplied by sorry, here it is not going to be t2 minus t1, it is going to be t minus t2. Okay, here also I'm sorry, so it is not t2 minus t1, because T2 is which temperature? This is going to be the temperature T2, right? This is going to be the temperature T1. We are finding out the temperature T. So T2 minus T I should be having over here. Here I should be having T2 minus T, and here I should be having T minus T1, because T is greater than T1. Now substituting the same, I will be getting K multiplied by T2 is 373 minus T I have to find out. It is going to be equal to K2. K2 is 180 multiplied by T minus 273. Is this what I'll be getting? Now the value of K can be taken 385 multiplied by 373 minus T is going to be equal to 180 multiplied by T minus 27. You can solve for the value of T by multiplying, or you can take 180 to the other side and solve for T. T value you should be getting somewhere around 340 Kelvin. This will be your final answer. This is the answer you should be arriving. Let us move on to the other two modes of heat transfer. We had three modes of heat transfer. The first one was conduction. We discussed about conduction. The next is convection, and then we have radiation. Convection. Thermal energy transferred by the movement of fluid from one region to another is called convection. Familiar examples are boiling of water, flow of blood in the body, or air currents. Next, we have radiation. Radiation is the process in which heat is transferred from one region to another region without the necessity of any intervening medium. We need not have any medium, still the heat is going to transfer in case of radiation. Next, we have properties of thermal radiation. We have six properties. They travel along the straight line with the speed of light. Thermal radiation travel along a straight line with the speed of light. They can always travel without a medium, meaning that they can travel in vacuum as well. They need not require any medium to travel. The third one is they do not heat the intervening medium through which they travel. The fourth one, they can be reflected and also refracted. They exhibit the phenomena of interference, diffraction, and polarization. They obey inverse square law, meaning the intensity is inversely proportional to the distance from the source. Next, we have about black body radiation. Body which absorbs the entire radiation, incident radiation on it is called a black body. It is an ideal radiator. The radiation emitted by a black body is called black body radiation. As simple as that. Emissive power. Emissive power of a body is defined as ratio of quantity of thermal radiation emitted per second per unit area of the surface. Absorptive power is going to be defined as the ratio of quantity of thermal radiation absorbed per second per unit area of the surface. Emissive power and absorptive power, the definition are alike. Only thing you have to replace is here it is going to be emitted, here it is going to be absorbed. Kirchhoff's law of radiation. The Kirchhoff's law of radiation says that the ratio of emissive power to the absorptive power is same for all the bodies at given temperature and is equal to emissive power of the black body at that particular temperature. Or you can tell the absorptive power is going to be directly proportional to the emissive power. If emissive power is taken as E lambda, absorptive power is taken as A lambda. When you divide E lambda over A lambda, you will be getting the value of K, which is going to be a constant. Okay, and that K is going to be the emissive power of a particular black body at that particular temperature. We will be ending up with Stephen's law for today's class. The energy U of thermal radiation emitted per unit time by a black body for a unit area is given by Stephen's law. It is U is equal to sigma T raised to the power 4, where sigma is a universal constant known as Stephen's constant. The energy U is given by sigma multiplied by T raised to the power 4. We have a last problem for today's class. Problem of 5. Black body of surface area 10 raised to the power minus 3 meters square is heated to 127 degrees Celsius and is suspended in room at the temperature 27 degree Celsius. Calculate the rate of loss of heat from the body to the room at this instant. Okay. Now, let me start by writing down whatever is given in the question. They are talking about area. Let me write area A, which is going to be 10 raised to the power minus 3 meter squared. We have temperature T. T is going to be 127 degrees Celsius, which can be written as 173 plus 273, right? 400 Kelvin. I have got the value of A. I have the value of T as well, right? I have one more value of T, which is going to be how much? It is going to be 27 degrees Celsius. So this is the higher value. I can take this as T2. The other one, T1, can be taken as 27 degrees Celsius, which is 27 degree plus 273. It is going to be equal to 300 Kelvin. 300 Kelvin. Next, calculate the rate of loss of heat from a body to the room at this instant. This is the question. All right. Sigma is a constant, even that will be given. Let me make a note of that. 5.67 into 10 raised to the power minus 8. This is going to be the value of sigma. Now, from Stephen's law, I can write that U is going to be, you should be taking the capital U. U is going to be equal to sigma raised to the power, what is the value? T to the power 4, right? So T raised to the power 4. Now, should I be adding anything over here? Should I be adding anything over here? Yes. Here it is taken for unit area, meaning that actually this formula is U is equal to sigma A T raised to the power 4, right? Per unit time divided by T. Actually, this is the formula, but we are taking unit area. So A will be equal to 1. Even T we are taking as unit time. That is the reason why A and T are not visible in this formula. Okay. Now, U is equal to sigma multiplied by T raised to the power 4. Here, it is not unit area. In this case, it was unit area. Here, it is not going to be your unit area. I can write the heat loss, U. U is going to be just the heat. Okay. You can take as U or E also. Anything you can take. That is going to be equal to sigma A T raised to the power 4. Now we have two temperatures that I can take T2 minus T1. That is the difference in temperature. Substituting the same, I will be getting the value U is equal to sigma. What is the sigma? 5.67 multiplied by 10 raised to the power minus 8 multiplied by A. A is 10 raised to the power minus 3 multiplied by T raised to the power 4. So I can write over here T is the difference in temperature, or I can write this as delta T as well. Delta T raised to the power 4 is going to be T2 raised to the power 4 minus T1 raised to the power 4. So here I can write 400 raised to the power 4 minus 300 raised to the power. Okay. When you solve, you should be getting the final answer as 1. This is going to be the heat which is going to be lost from the body to this room. Okay.